Hello, dear colleagues. My name is Artur Rusinov. Today I will talk about application of the point-like contact model, in particular, resistance simulation of the single magnetic domain wall. Imagine that we have nanowire. It can be not only nanowire, it can be nanojunction, and in the middle of the nanowire we will have a point contact, that is geometrical constriction or defect with its own resistance. So the total resistance of the nanowire will be resistance which coming from segments and plus resistance from this defect. This nanoconstriction may have domain wall or may not. So let me show you the difference between the systems if it have the domain wall or without. So the main difference will be the following. As if we have the different magnetization alignment from the left and right side, the density of states for the spin up, for example, will be different, especially if we will use approach if electron spin conserved due to this transition through the domain wall. And in other words, we have a barrier, and the total resistance of this point contact will have the geometrical reason of the scattering, additional scattering plus the additional scattering from the barrier coming from the difference between spin bands on the Fermi level. And the model is following. So we have to divide the voltage on the total current. The problem is how to find the current. But let me, in the beginning, show you which barrier better to use for the domain wall. So here I used the linear approach of this barrier. The magnetization switching approximately happened by the linear law. I'm agree that there is a more precise models of this magnetization switching and inside the domain wall. And for example, hyperbolic tangent or arcsine from hyperbolic tangent of this argument. But unfortunately, the solution for this more exact behavior solution of the Schrödinger equation is much more complicated than for the linear one. For the linear one, it is well-known solution which is used for this work based on the Airy functions. Regarding parameters for the spin up and spin down bands, they can be found from literature on the Fermi level. For the cobalt and for the nickel, parameters approximately can be taken like this. In experiments, you can find the photoemission spin resolved spectroscopy. The values for the majority, for example, is around 1 inverse angstrom. So that is similar that I will use in my case. So the problem of the point contact is very important because in range of this model can solve numerous physical problems. There are well-known non-magnetic point contact models in literature by Wechsler, by Nikolic, by Microjudin. They all consider a non-magnetic point contact with radius A and give the solution. But starting from 2001, you can find in literature the solution for the magnetic point contact. And the first one was the uniform junction for the magnetic point contact developed by Taguirov, Vodopedov, and Defetov, combining two works, Zaitsev boundary conditions and transport theory of the following by Reimer and Smith. The kinetic equation for the quasi-classical green function was derived. This system of the equation was solved and found the solution. Later, within my PhD work, I developed the model for the more general junction, where the left and right sides of the junction can be different magnetic or non-magnetic materials. Unfortunately, the diffusive limit of these two works was not precisely exact as a well-known Maxwell solution. And last year, the final approach was found where the both limits, diffusive and ballistic one, satisfy to the Maxwell and Charvin limits exactly. So let me show the results of the last work. First of all, this is a question how to calculate the current for the point contact. If we know the transmission coefficient through this contact, we can calculate the current. This current includes variables, which is like basic fundamental physical parameters, like wave number on the Fermi level, the area of the cross-section area of the point contact, voltage, and so on. So it includes the integration over the Bessel function and a few terms. First term is a so-called ballistic term, or if the transmission coefficient is not equals 1 or not equals unity, it becomes a tunnel responsible term, and also includes two diffusive terms. They are complicated integrals which also include inside the transmission coefficient. The red color shows the dependence from point contact radius. So if we assume that the transmission coefficient equals unity and left and right sides are non-magnetic and symmetric, so we derive the equation number 2. For this, we have to double this equation because spin up is equivalent to the spin down and divide the current on the voltage. You can see that the ratio between mean free path and the radius, if it going to the infinity, this integral becomes equals 0, and we have the exact Charvin solution, Charvin conductance. When the k goes to the 0, so this integral have the magic limit that all expression becomes equals to the exact Maxwell conductance. And this is a benefit of the work. How to prove that this equation 2 is works, and how to prove, for example, that ballistic or tunnel responsible term is works. Just compare with find problems in literature and compare the experimental results with theoretical calculations. For example, using the only ballistic tunnel responsible term, the so-called anomalous tunnel magnet resistance was well explained for the magnetic tunnel junctions with embedded nanoparticles. Plus, non-magnetic systems like golden nanocontacts also give a nice fitting for the theoretical curve. It was found that K Fermi around 0.9 inverse angstrom very well suited for explanation of these golden nanocontacts for the ballistic, for the quasi-ballistic, and for the diffusive regime of the conductance. Very interesting that a little later I found the work where the photoemission spectroscopy of the golden Fermi surface shows that the ideal fitting for this surface also is around 0.9 inverse angstrom. That coincides with my theoretical finding. So, so the next step is how to prove that total works, complete expression of equation 1 is works. So the next step is find the resistance of the domain wall in the nanowire. So to find it, we have to find the difference between the resistance of the segments plus resistance from the nanoconstriction with domain wall, and the difference and the same resistance of these segments plus resistance without domain wall. So the difference gives this one very simple equation where the resistance can be calculated by equation that was shown in the previous slides. We can find the segmented domain wall resistance for the segment nanowire, for example, cobalt nickel, or for uniform nanowire, cobalt cobalt, nickel nickel. But there is one condition. According to the work following published by Bruno, it was shown that there is a threshold below which our domain wall becomes constrained. So it means that domain wall width have to be equals or follow the diameter of the nanowire, which is close to the diameter of point contact. So if a diameter of the nanowire is larger, and diameter of the point contact is larger than this threshold, domain wall width is constant. So, and the first point which I found in literature was the green one, 1.2 ohms for the single domain wall resistance for the nanowire with 80 nanometers, cobalt nickel segmented nanowires in this work. And the blue curve shows the whole range if we will theoretically change the diameter of this kind of nanowires. Unfortunately, they show only fixed diameter. And you see that before this threshold, when the diameter is relatively small, there is some oscillation of the domain wall resistance. That is not an integrational mistake. This is due to some oscillations. After, so if we pass through this threshold, the domain wall width is constant, and the domain wall resistance is still continue rapidly drop with the diameter. But there is a ballistic regime of the transport, quasi-ballistic, and diffusive regime. So all experimental data mostly lies in the diffusive regime. So, what is the difference between black, blue, and magenta? Magenta, for example, curve number 1 is given as a reference for the constant domain wall width, around 10.6 nanometers. Black one is just attempt to play with the mean free path. For the black one, we have the fixed mean free path ratio between spin up and spin down around 3. If we will use the another ratio for the segmented nanowires, for the cobalt 3, for the nickel 4, it will be a blue curve, and for the first curve, magenta curve, is taken around 4, just in case, just to see what is the difference. Now the next slide shows the mostly oriented for the red experimental data. Yes, this is from different sources for different materials, but it's hard to find the data for different diameters and for the same materials or segmented nanowires with different nanowires. So here clearly for the uniform nanowires, you can see clear oscillation behavior of the domain wall resistance as a result of difference of the nanoconstriction with domain wall and without. So let me show the zoom of this figure. So again, I found the, just in case I shift the threshold as large as possible to show where the oscillations decreases, and found that for the nanowires larger than 15 nanometers, the oscillation suppressed and becomes negligibly small. For the cobalt nanowire, the threshold is around 10 nanometers. So if consider the cobalt-oriented nanowires, clear cobalt nanowires, so probably the oscillation will happen by black curve and then disappeared after around 10 nanometers in diameter. So, but anyway, this oscillation exists, and this is a recipe how to simulate the single domain wall resistance. The program's available online. You can download and use. And my conclusions are following. So the novel domain wall resistance model is built with a constraint domain wall that have the functional dependence from domain wall diameter below the threshold. The model reproduces the ballistic, quasi-ballistic, and diffusive transport, completely utilizing equation 1 and prove it precise. That is very precise. So relatively large oscillation of domain wall resistance is found at the threshold less than 15 nanometers. And the reason of the slope variation of the potential energy profile is the reason of this oscillation. So thank you for your attention.